So we can combine these gas variables once, yes, but what about second combination? What if we wanted to relate all four of our gas parameters of pressure, volume, temperature, and number of moles to each other? In so doing, we can take advantage of these 5 gas laws. We know, for instance, that from Boyle's law, pressure times volume is a constant. Maybe we'll let some variable that we haven't chosen yet stand in for that constant, like R. We know from both Amundsen's law and from Charles' law that as temperature increases, pressure or volume increase. And we know from Avogadro's law that as number of moles of gas particles increase, volume increases. We can tie all of those quantities together into one singular equation that no longer shows us a change, but rather a dependence of each one of these parameters on each other. Pressure times volume is equal to number of gas particles times the ideal gas constant R times T. These 4 variables are tied together with a fundamental universal constant that's so prevalent that it crops up in all sorts of calculations that might not have anything outwardly to do, seemingly, with gas. This constant, R, the ideal gas constant, has a value that takes on units that are most commonly used to measure pressure, volume, number of moles, and temperature. Namely, atmospheres for pressure, liters for volume, number of moles for N, and Kelvin for temperature. The value for this ideal gas constant is 0.08206. The units are liters times atmospheres per mole per Kelvin. Liters, atmospheres over mole, Kelvin. This equation, PV equals nRT, or Pivnert, as some students like to remember it by, is called the ideal gas law. This is the crux and central idea that ties together all 5 of these empirical or experimentally based gas laws. The ideal gas law is pertinent and relevant to all so-called ideal gases. Ideal gases, like their name suggests, behave ideally, which means they don't interact. More explicitly, ideal gases conform to the rules of the kinetic molecular theory of gases, which we'll explore in just a few minutes. And more globally, in this course, we will only consider ideal gases, and will reserve a discussion of real gases that don't conform to these rules in a future class. Overall, though, we'll include the ideal gas law, or Pivnert, as sort of the overarching equation from which we beget all of these others. Before we move on to talking about the kinetic molecular theory of gases and how Pivnert relates to these other quantities, let's do some examples of how to use PV equals nRT, the ideal gas law. Suppose, for instance, that we wanted to know something about a gas at a benchmark set of conditions. Such a benchmark set of conditions might be referred to as standard conditions. And in particular, standard temperature and pressure, or STP for short, represents a benchmark for tabulated values. Rather than measure the properties of a gas at all possible combinations of temperature and pressure, it's convenient if we only restrict ourselves to measuring a a certain temperature and a certain pressure, and then extrapolate from there. Whenever we see STP, or standard temperature and pressure, that should tell us that the temperature is presumed to be 0 degrees Celsius. And because all of our gas laws are predicated upon Kelvin temperature, that's equivalent to 273 K. And furthermore, the pressure should be presumed to be 1 atmosphere. Standard pressure is atmospheric pressure under normal conditions. 1 atmosphere. Reiterated down here. So let's determine the volume that 1 mole worth of gas occupies at STP, these standard conditions of temperature and pressure. And once more, we can make a list of things that we know. Implicitly, by being told that conditions are at STP, standard temperature and pressure, we should recognize temperature is 273 K and pressure is 1 atmosphere. These conditions aren't changing, which should signal to us that we're likely going to need to use the ideal gas law. The ideal gas law, Pivner, is the only equation in which we don't have a 1 and a 2. We have a direct correlation between pressure, volume, temperature, and number of moles, given by the ideal gas constant, R. Here, we'd like to know volume, given that the number of moles of gas particles is presumably exactly 1. From this information, we'll identify again our ideal gas law as the relevant tool to use. We're given pressure, temperature, number of moles, and a gas constant as a constant value. So we can plug directly in with all of the information provided and solve for volume. When we do so, we'll have to divide both sides by 1 atmosphere, which is trivial. All of our units, aside from liters, will cancel. And we should come up with 3 significant digits at the end of all of this. Keeping 3 significant digits, we get this answer: 22.4 liters. That means that our gas, with contents that tally to 1 mole total, occupies a volume of 22.4 liters. So, that might beg the question, what gas is this? Well, he didn't specify up above. In fact, we've rarely specified identities of gases as we've moved through this chapter thus far. All told, the identity of the gas really doesn't matter here. So far, all of these equations are universally applicable. In fact, our ideal gas law has a universal constant R already contained in it, and it really doesn't matter what gas this applies to. This is true for any ideal gas. Thus, we referred to this volume, this 22.4 liters, as the standard molar volume of a gas. In other words, 1 mole of any gas, regardless of its identity, so long as it behaves like an ideal gas, will occupy 22.4 liters worth of volume under standard conditions of temperature and pressure.